10,000 cement bags filled every hour. Impossible without chemistry so precise that a single miscalculation could halt the entire line. Hidden inside the process are minute-by-minute analyzer loops, real-time measurements, and algorithmic controls that cut critical volatility by more than half. This relentless data dance is the difference between seamless production and catastrophic shutdown. But what does it really take to keep 10,000 bags flowing without ever skipping a beat? At Plant C, the heartbeat of cement production pulses through a network of sensors and control screens. Every minute, Crossbelt XRF and PGNAA analyzers scan raw limestone and clay as they move along wide conveyors toward the blending silos. Near-infrared sensors, abbreviated NIR, are tuned to detect subtle shifts in mineral phases and moisture, and they capture readings in less than 60 seconds. These measurements are not just numbers, they are the real-time chemical fingerprint of the entire feed stream, tracking calcium oxide, silicon dioxide, aluminum oxide, and iron oxide with remarkable speed and precision. On the control room dashboard, each new scan triggers a fresh set of calculations. The lime saturation factor, known as LSF, the silica modulus, and the alumina modulus appear as live trends, their lines rippling across the screen. A sudden spike in silica or a dip in alumina sets off a cascade of algorithmic adjustments. Proportioning valves shift, corrective fines are dosed, and the flow of raw materials is steered back on course, all within the next minute S cycle. The system S latency from analyzer reading to automated valve action rarely exceeds 3 minutes, a pace that keeps the entire process tightly synchronized. Operators at their consoles monitor these loops with practiced attention. Their screens show not only the latest analyzer values, but also alarms, historical trends, and override options. When a sensor drifts or a reading falls out of the expected range, the system flags it instantly. Operators may trigger a manual cross-check, pulling a grab sample for lab XRF analysis, or initiate a brief recalibration routine. While the algorithms handle routine variability, it is human judgment that steps in during outlier events, such as a sudden change in quarry feed or unexpected moisture from a passing storm. The impact of this live analyzer loop is measured in stability. With minute-by-minute correction, LSF swings are cut by about 70%, and free lime variation is nearly halved. This steadiness translates directly to kiln performance, fuel savings, and uninterrupted bagging at full speed. The data flow is relentless, but it is also transparent. Every scan, every correction, every override leaves a trace in the system log, forming a digital record of chemistry in motion. In this environment, the slightest deviation is caught and corrected before it ever reaches the kiln, ensuring that the line never stops moving and the bags keep filling hour after hour. On the control room's main display, 3 formulas dominate every decision: lime saturation factor, silica modulus, and alumina modulus. Each value is calculated in real time using the latest analyzer readings. Lime saturation factor, called LSF, is derived by dividing calcium oxide by a weighted sum of silicon dioxide, aluminum oxide, and iron oxide. The silica modulus compares silicon dioxide to the sum of aluminum oxide and iron oxide. The alumina modulus measures the ratio between aluminum oxide and iron oxide. These numbers are not just math, they are the levers for every raw meal adjustment, each one tied directly to a physical actuator somewhere in the plant. The control system runs on a hierarchy of algorithms. At its core, proportional integral derivative loops, often called PID loops, track each main oxide, making small, continuous corrections to keep the set points steady. As the raw mix becomes more complex, Model Predictive Control, or MPC, looks ahead. Model Predictive Control simulates the impact of multiple changes at once. then calculates the best combination of valve moves to keep all three moduli inside their narrow bands. The result is a raw meal that rarely drifts more than a fraction of a percent from target, even when the quarry feed shifts or a conveyor hesitates. Every correction triggers a physical response. If the silica content climbs, the algorithm opens the clay valve by a few percent or calls for extra corrective fines. If the LSF dips, limestone flow increases. These actions ripple through the plant as motors hum, feeders adjust, and blending silos rebalance. The system logs every move, each valve position, every analyzer reading, and the calculated effect on free lime and kiln stability. Over time, the impact is clear. Free lime variation is cut by half, and the risk of overburning or underburning in the kiln drops sharply. Yet the algorithms never run entirely on their own. When a sensor reading jumps outside its expected range, or when a sudden rainstorm throws off moisture content, operators intervene. A veteran engineer may override the algorithm, locking a feed valve or shifting the target set point until laboratory results confirm the new baseline. These moments are recorded alongside automated actions, forming a complete digital trace of both machine logic and human judgment. The interplay between algorithm and operator is what keeps the process resilient, able to maintain thermal steadiness and throughput even when conditions turn unpredictable. Inside Plant A, the preheater tower rises above the main kiln hall, its 6-stage cyclone stack humming with the sound of gas rushing at nearly 40 meters per second. Every second, hot exhaust from the kiln base surges upward, meeting a steady rain of raw meal falling from the top. These cyclones are engineered for speed, each one shaped and sized to maximize contact between hot gas and solid particles, pushing the temperature of the meal from ambient to over 800 degrees Celsius in less than 5 seconds. Operators monitor the process from a control room lined with infrared scan monitors. Thermal images update in real time, painting the cyclone walls in gradients of yellow and red, each color shift revealing subtle changes in heat transfer or material flow. When the gas velocity slips below 30 meters per second, heat exchange slows and the risk of meal buildup rises. Too much velocity and the meal is swept through before it can fully calcine, wasting fuel and leaving unreacted material downstream. At optimal speed, the meal is suspended just long enough for carbon dioxide to be driven off, transforming it into a reactive powder ready for the kiln. But even the best design faces challenges. A sudden spike in sulfur or chlorine from the raw mix can trigger sticky deposits, narrowing the cyclone throats and raising pressure drop. The infrared scans pick up these hotspots first. A bright flare at stage 3 signals a potential blockage. During a tense shift in May 2019, a sharp rise in cyclone temperature set off alarms. The crew sprang into action, toggling airflow dampers and deploying targeted air bursts to break up the forming deposit. WhatsApp threads from that night show a minute-by-minute account. Increased tertiary air to the upper cyclones, a quick water burst at stage 4, and constant thermal checks until the blockage finally released. The entire intervention lasted 36 hours, but the line never stopped. Avoiding a shutdown saved more than $250,000 in lost production and kept the kiln feed stable for the next batch. In this environment, every second counts, and the margin between smooth flow and costly downtime is measured in meters per second and in the vigilance of the team watching the screens. Maria Lopez stands by the kiln console, her eyes on a set of flame profile graphs. The KHD Pyrojet burner at Plant B is her domain, a complex assembly of coaxial tubes, air rings, and fuel lances, all engineered for precision. The goal is not just to ignite fuel, but to sculpt a flame that runs 1,450 degrees Celsius at its core, creating the right melt zone for clinker formation. Too short, the meal underburns. Too long, the kiln lining risks spalling. Maria adjusts the primary air, a cool, high-velocity jet that cores the flame, while the secondary and swirl air jets wrap around it, shaping the plume's length and turbulence. Her protocol, refined over years, calls for a strict air split, 60% secondary, 30% primary, 10% swirl for standard coal. She tweaks these ratios in real time. When the raw meal's silica modulus drifts up, she narrows the flame, boosting peak temperature and accelerating melt. If the feed runs wetter, she extends the plume, allowing more time for evaporation before the meal hits the hottest zone. Each adjustment is logged, every air valve move tracked against the live kiln shell temperature. The pyrojet's annular air rings allow her to keep the high temperature zone precisely inside the kiln core, sustaining a 22% liquid phase, enough to bind the clinker minerals, but not so much that the lining overheats. That balance protects the refractory and shapes the crystal growth that determines final cement quality. Supervisor reports from 2017 onward show a 15% drop in refractory wear after Maria Lopez's protocol was adopted. Her video journals capture the rhythm of her work. A glance at the flame camera, a tap on the human-machine interface, a check of the liquid phase indicator. She mentors junior technicians in reading the subtle cues, a slight shift in flame color, a tremor in the temperature trace. Those signals tell them when to intervene and how to intervene so the kiln keeps running steady. The result is a kiln that runs steady, with the melt zone held tight and the risk of deposit formation kept at bay. Maria Lopez's approach has become the reference, ensuring the chemistry set upstream is realized as stable clinker at the heart of the process. Inside Plant E, warning signs arrive in subtle waves. A pressure spike on the kiln exhaust, a faint uptick in temperature near the cooler throat, and then a slow, relentless rise in gas velocity. These are the hallmarks of a snowman forming. A mass of alkali and chloride salts fused with dust, coalescing into a hardened obstruction at the kiln's front end. The volatile cycle drives this buildup. As kiln gases carry sodium and potassium vapors forward, they cool and condense, binding with sulfates and fine meal to create a sticky, low-melting crust. If left unchecked, this crust can balloon into a full blockage, threatening to choke off clinker flow entirely. The maintenance log from February 2022 captures the crisis in real time. At 2:14 in the morning, the control room logged a sudden drop in cooler draft. By 2:31 in the morning, the internal camera confirmed a snowman nearly 1 meter wide perched at the discharge. Plant E maintenance foreman Luis Herrera called in his team. Luis Herrera recalls that every minute counted and they had less than an hour before the line would grind to a halt. The response was fast and deliberate. Operators slowed the kiln, shifting the thermal gradient to weaken the deposit's grip. Carbon dioxide was injected directly at the snowman's base, quenching the surface and fracturing the crust. Real-time gas monitors tracked oxygen and carbon monoxide spikes, alerting the team to any risk of combustion instability. Within the hour, Luis Herrera's crew positioned a water cannon, guided by live camera feeds. The first burst cracked the shell, and the second sent fragments tumbling into the cooler. Over the next 36 hours, the team alternated between controlled air bursts and targeted carbon dioxide injections, gradually restoring full flow. Each intervention was logged and each pressure rebound was noted in the rescue record. By the end of the shift, the snowman was gone. The line was open, and the plant had avoided a costly shutdown. The maintenance team's toolkit, thermal imaging, gas quenching, and camera-guided demolition had once again kept production moving. Luis says there is no single fix. It is vigilance, teamwork, and knowing exactly when to strike. Inside the cooler hall, the transformation of clinker is governed by airflow and timing. As red-hot nodules drop from the kiln at over 1,450 degrees Celsius, they spread across a moving grate, sometimes a walking floor, sometimes a crossbar system designed to keep the bed even and prevent bottlenecks. Beneath the surface, a network of aeration zones delivers carefully measured blasts of air. Each zone is tuned to hold the clinker at a controlled temperature, typically between 500 and 600 degrees Celsius, for just the right dwell time. This pause is not arbitrary. Slow cooling at this stage allows belite crystals to grow, while a rapid quench later in the process locks in alite, the mineral responsible for early strength. Operators monitor temperature sensors and pressure readings, adjusting airflow to avoid hot spots or cold pockets. If the clinker cools too slowly, grindability suffers and strength may drop. If it cools too fast, the mineralogy shifts, with possible consequences for both milling efficiency and final product performance. The cooler exhaust, still loaded with heat, is routed to a waste heat recovery system. Here, waste heat and energy are captured, typically yielding 25 to 30 kilowatt hours per ton of clinker, and redirected to preheat incoming air or generate electricity for the plant. This loop not only improves fuel efficiency, but also stabilizes the power supply, closing the energy circuit that began in the kiln. The result is a process where thermal management, mineral formation, and energy recovery are inseparable, each reinforcing the plant's ability to fill thousands of bags every hour without interruption. Grinding is where energy and chemistry collide. In the finish mill, the choice between a vertical roller mill and a ball mill is a matter of both economics and product quality. Vertical roller mills operate in the 9 to 15 kilowatt hours per ton range, while traditional ball mills consume nearly double that, 20 to 30 kilowatt hours per ton, especially when chasing higher blane fineness. The pressure to push blane values above 3,500 square centimeters per gram is real, but each extra increment comes at a rising energy cost. Operators must weigh the diminishing strength gains against the steep curve of power demand. Grinding aids like triethanolamine and triisopropanolamine have become essential tools in this calculus. Dosed at fractions of a percent, these additives coat cement particles, break up agglomerates, and smooth flow through the mill. The result is a measurable drop in energy use. Plant trials confirm savings of 10 to 15%, with specific energy in ball mills falling from 24 to as low as 20 kilowatt hours per ton. In vertical roller mills, savings are slightly lower but still significant, often enabling a 200-point increase in blane for less than 1 kilowatt hour of additional energy. The impact goes beyond energy. Particle size distribution tightens, with more grains in the optimal 3 to 10 micrometer range and fewer coarse or ultra-fine outliers. Early strength improves and flowability rises, allowing mills to run faster without risking blockages or quality slips. Still, the balance is delicate. Overdosing can raise water demand or blunt long-term strength. In the end, the right combination of mill type, grinding aid, and blane target is a moving target, recalibrated with every shift in feed or product specification. This is particle engineering in real time, with every adjustment logged and every outcome measured in throughput, cost, and the steady filling of bags on the line. At Plant G, the push to cut carbon runs headlong into the realities of chemistry and economics. On the lab bench, LC3 blends made from calcined clay and limestone promise up to 50% clinker reduction. This single change slashes process carbon dioxide by a third and trims production costs by as much as 20% per ton, provided the raw materials are close at hand and consistent. The research and development chemist recalls, "Scaling LC3 is our best lever for near-term carbon dioxide reduction, but rheology and performance quirks challenge daily operations." The new blend ran thick, forcing operators to adjust water dosing and mill speed until the line stabilized. After a week of tweaks, the output held steady at 10,000 bags per hour, but only after close coordination between lab and production teams. Beyond supplementary cementitious materials, the industry's gaze turns to carbon capture and storage. Recent pilots in Europe and the United Kingdom have achieved over 90% kiln carbon dioxide capture using solvent or membrane systems. But the economics are daunting. At Company H's site, projected capital costs rose from $60 million to $145 million in 3 years, with annual operating expenses running $20 to $40 per ton of carbon dioxide captured. Internal audits warn that full plant carbon capture and storage could double cement prices unless backed by major policy incentives. Executive memos urge caution, noting that while technical feasibility is proven, the business case remains fragile. For now, most plants focus on scaling supplementary cementitious materials and alternative fuels, practical steps that deliver real emissions cuts, while watching carbon capture and electrification as long-term bets, contingent on both technology breakthroughs and regulatory support. Every ton of cement carries a carbon footprint, over 3 billion tons of CO2 each year, now under global scrutiny. As cities rise and climate targets tighten, the pressure to decarbonize cement intensifies. Real-time chemistry and process innovation aren't just technical feats, they are the front line in a race to reinvent what builds our world. The next breakthrough will define tomorrow's skylines.